Hey everybody, my name is Justin Polite. I'm in Kendall Jacobs Math 1100 class, and today we're going to be working on a question on Seminar 4, and we're just going to get right into it. So here, I actually, on Google Docs, I created a document for Seminar 4, and we're just going to kind of follow along with this document, and which is basically a step-by-step in order to solve the problem. So we're just going to go ahead and jump right into it. So mine was challenge 5, and it reads Kendall's donuts come in boxes of 6, 9, or 20. What is the largest number of Kendall's donuts you cannot buy? So my first impression was, well, if 6, 9, and 20 are my boxes of donuts, my first thoughts were that 19 is my largest number of donuts I cannot buy. I can buy a box of 20, eat one donut, and have 19. The rules are that you can buy either a box of 6, 9, or 20, and there is not a limit to however many boxes you can buy of one particular or all three. You can buy more than one box of each quantity, so I can buy a box of 6, 9, and 20, or two boxes of 6 and one box of 20. At this point, it almost seems like there is like an unlimited amount, an unknown answer of the largest number of Kendall's donuts I cannot buy. So for step number 1, find a direction to go and write down formulas or references to help. So what I first did is I wrote down the number of boxes, 6, 9, and 20 in a vertical column. And then aside from each number, so 6, I wrote plus 6, plus 6, plus 6, plus 6, and then I equaled it out to 30. And I did that for same for 9 and for 20. And the reason why I did this is kind of something that I'll explain a little bit later. But basically, it was just kind of like a little reference. That way, I could kind of when I'm gonna do the next step, I could kind of like just look at it and be able to have a quick reference, help me out, be a lot quicker without having to it's kind of like a like a calculator, I guess, a workload, to help me out with the workload. So number 2 is write and go through table. So on this step, I write down numbers 1 through 25 to start with to see if I can find any patterns by using my inductive reasoning skills. The way I do this is if I write down 1 and I look at the boxes of donuts I have to choose from, I ask myself, is there any way that I can get to one donut without eating any, but by only buying boxes of the amounts provided, 6, 9, or 20? And no, there is not. So what about 2? Can I get to 2 with 6, 9, and 20? No, I can't. Can I get to 3? No. How about 4? No. 5? Nope. 6? Yes, I can. There's a box of 6. All right, so I can get to 6. I can buy one box of 6 donuts. This is the strategy I use to look for patterns so I could hopefully have something to work with. Below here is the table that I constructed. It's just like a little chart, basically. In reference to what we were talking about just a little bit earlier about 1 through 25 are basically the first ones that I worked with, the numbers I worked with. For instance, the 1 through 70 that I have located on this paper are basically X number of donuts, and the beside the hyphen is going to be no, it cannot work, or yes, it can work. So what I mean by that is like, okay, if we have one donut, can we get to, with six donuts, or 9 or 20, can we get to 1? And no, we can't. So if you look at the chart, the first one at 6 is yes, so we can get there by one box of 6. 9, yes, one box of 9. 12, yes, we can, two boxes of 6. 15, yes, one box of 6, one box of 9. 18, yes, we can, two boxes of 9. 20, yes, we can, one box of 20. 21, yes, we can, that's two boxes of 6 and one box of 9. And 24 we can, that's going to be 4 boxes of 6. And then we get to 25. All of the others are no. No, we cannot get that number with those given boxes that we have. So then I looked at it and I said, okay, well, there's nothing that's really, the same or similar, so I'm going to go ahead and carry on. So I went from 26 to 51. And from 26 to 51, you can notice in the chart that, there was more between 26 and 51 that were able to pass, that we were able to buy, to get from those boxes. And if we look a little bit closer, when we get to 44, just before 44, 43, so right in this area after 44, I when we got to 51, it just seemed like there was a lot more. So I went ahead and went a little bit further. So basically, I went from 51 to 70. And if we can look at here, all of the reds on here are yes. So yes, from 44 to 70, they were all yeses. And that kind of basically threw a big flag at me. So this gets us to our next question here. Sum up the chart. After looking at the chart I could notice that the differences between yes, I could get to that number using the boxes of donuts 6, 9, and 20, and no, I cannot get the number using the boxes of donuts 6, 9, and 20. Numbers 1 through 25 seem to have a ratio of 8 to 25 yeses to 17 to 25 no's. Numbers 26 to 51 had a ratio of 19 to 25 yeses to 6 to 25 no's. Numbers 52 to 70 had a ratio of 18 yeses to 0 out of 0 no's. I stopped trying numbers after 70. Number 5, evaluation. After evaluation, I could notice the different patterns between the numbers of donuts between 1 and 70. Less than half of donuts 1 through 25 were able to be bought from the boxes of 6, 9, and 20. More than triple the amount of donuts 25 through 51 were able to be bought from the boxes of 6, 9, and 20. All of boxes 52 to 70 were able to be bought using boxes 6, 9, and 20. Number 6, review. At this point, I can see that after number 43, every number up to 70 was able to be bought using the boxes 6, 9, and 20. How do I know that 43 is a lucky number and say 1001 is not a number that will work? Inductive reasoning is finding the patterns to the problem, and deductive reasoning is finding the solution. So we are 75% done with the problem. We still need to be sure that we are 100% correct. Number 7, review table for more patterns. After reviewing the table again, I noticed that there was an easier way and faster way to solve the problem using the table that I provided. Instead of going through the numbers of 6, 9, and 20 to find a possible way to get X donuts, I could have looked for patterns within the numbers of X donuts to speed up the processes or help me solidify my answer of 43 donuts being the largest number of Kendall's donuts I cannot buy. So I could use the chart I made at the very beginning. So 6 plus 6 plus 6 plus 6, and then the 9s and the 20s. So basically, it is easy to look at 6 and 9 and 20 and plot them on the chart. I could add all three up and get 35 and chart it. I could chart whatever 6 plus 6 is, which is 12, or 6 plus 6 plus 6, which is 18. I could go through the chart with these using 6s, 9s, and 20s, but those numbers alone aren't going to get the answers to them all. So what is another way that I could find the answers? What about adding 6 to an X numbered donut and see if it goes through? How about 44? We know that 44 can be obtained by adding 20 and 24. We can get 20 by a box of 20 donuts and 4 boxes of 6 donuts. Let's use 44 and add 6. Since we know 44 works, we can add 6 and we know that that number should also work. 44 plus 6 equals 50. What about 50 plus 6? If we already know 50 works and add 6, 56 should work too, and so on. After doing this trial and error method for deductive reasoning, we can conclude that the answer of 43 is the largest number of Kendall's donuts that you cannot buy. In conclusion, it is an easy question, but hard to see the patterns if you do not look between the lines. This question read, Kendall's donuts come in boxes of 6, 9, or 20. What is the largest number of Kendall's donuts you cannot buy? I thought there was more to the question in order to solve for an answer. I did seek help during steps along the process by going to the math lab and going to Kendall's Donuts downtown to see if they knew the answer, but they didn't. All they said was that you cannot eat any. So I just asked to speak to Kendall, and he was happy to help steer me in the right direction. The diagrams I drew helped observe the problem and point out what I didn't already know. Looking back at the completed diagram made things make more sense to me. And with that, basically comes to an end of this question. I thought it was a fun question. I like these questions. They're kind of hands-on, and they're kind of like related to the real world. Even though it wasn't easy to kind of like open the doors and go running with it. I was able to kind of use what I've learned so far in this class and kind of find a solution to the answer. So I enjoyed this question, and I hope you guys did too. Thank you.